Okay, hello everyone. Welcome to another Wolfram Language Design Review. We are looking at some new functionality related to diagrammatic computation, string diagrams, and other things like that. And this is, we did at least one previous meeting on this, and this is a follow-up. So,
Right. So this is substantially the same agenda from last time. There were a few sections we didn't get to, and there's also some people who are in the meeting now that weren't in the last meeting.
okay, should I rerun the Packlet install?
Yes.
Yep. And some of the stuff got spruced up for our lambdas effort.
Indeed.
That's right.
What is going on here? Should I continue waiting? What's happening?
I don't
Have
know.
something else running? No?
Well, maybe let me take a little look here.
We can start with the fresh kernel. It's better.
Okay, fine. I think I might have something else running, but with a different kernel, so. I'm a little concerned that my machine is being eaten alive by something else. Just check. Let me see. Oh my. Well, that's got like 30 cores or something. The fact that there's one thing running a crazy amount shouldn't hurt it. Okay. Let's launch in here. So we talked about last time. Yeah, I mean, this whole diagram name is still very much bothering me, but still. I also wonder if we couldn't get a little bit of, what's this? Error here. What is that? Anybody know?
I don't know, Nick.
Doesn't look like the Packlet related. I don't know any front-end dynamic shenanigans there.
Okay.
So maybe from the click to copies.
Perhaps.
Why are there click to copies? Where is there a click to copy?
On the label, the default, you can copy the.
Yeah, that's not working. Is this? So you have in fact got dynamic shenanigans going on.
Oh, it's just click to copy of the wrapper.
Well, so something went wrong with it.
Inside the graphics. It shouldn't be that problematic.
Well, okay, but it's a bug. So, okay,
Yep.
One thing we should do, probably sooner rather than later, is get some graphic design into these things, because this is looking. But let's take a look at what this all means. So here is a diagram called. Oh, for God's freaking sake! Every single time I hover over anything, I'm going to get one of these.
Is dynamic updating enabled for that notebook?
Oh, it wasn't.
There we go.
But the fact that there was that error is very wrong. So can somebody?
Sure.
Nobody from QA is here. So can somebody please bring that to them?
Okay. Yeah.
Yeah,
sure.
Okay. So this is, the thing is an A and the output is an X here.
Yep.
And this is input to output.
Yep.
And we talked last time about graphs with ports and the relationship between this and graphs with ports, if I remember correctly. This is like a single node of a ported, well, it's not really fully ported because this is, these are in order, right?
Mhm.
Yep.
And they can be named. They could be in an association. Is that a true statement?
We already considered those are names. Associations not needed. Well, it depends what you mean.
Well, why can't these ports? You're already thinking of these as the names of those inputs. Is that what
Yes.
you're
Yeah.
saying?
Yeah, there's basically a special port object that being created there. It has a name and a bunch of other properties.
What are the properties?
Well, for example, it encodes in itself whether it's going or outgoing from the diagram.
So should I take this and say, if I say input form of this, how horrifying is it going to be?
A bit. Yeah, there's those ports, and yeah, they have an association with them.
Okay, so how does this relate to the notion of a port that Charles has for the Graphs with Ports project? Charles, can you speak to that?
So at least for my, just on top of my head. So the diagram there, I just see it as a node, and you have, input port and output port. So for the graph report, we don't make that distinctions, right? So those distinctions are pretty much a notation you can store as a property for your port or for the node. So this seems to be a special case, a special specifications, as well as a special set of rules, so how you combine those diagrams, those nodes.
Right. So do you have a design yet for Graphs with Ports?
Yes, we did, and we discussed that last time, I think. Which
Okay,
was
well, is this compatible with that, or is this totally incompatible? Are we using up a port, the port name for something completely different? Yeah. Do you understand what I'm asking?
I'm not sure.
Well, with graphs with ports, we were going to have a vertex port symbol.
Okay, but I don't think these should be called ports. I don't see why you even have to mention port here. This is just a list of associations, isn't it? Input ports is a bunch of associations. Output ports is a bunch of associations. Why have a
Well,
wrapper?
it is conceivable that this port can be similarly annotated on the graph as in graph. Right. All this information can be annotation for underlying diagram. It doesn't have to be an object like this.
Right.
Okay, go ahead.
For a graph report, those are just annotation. But just a question here: those ports, do you make a distinction between the wire and the port, or is that the same thing? Because
we don't have wires stored in the object. We don't have explicit wire construction, basically. We only have ports.
So what is port dual?
It basically tells you whether it goes into a diagram or outgoing from the diagram. The direction, basically.
I think there's got to be a better way to do that. I mean, look, I really don't think we should be using, particularly not in this, defensive design of this object would imply that we should have just associations here, no extra symbols.
Yes.
Okay, so I think
It's
that's
kind
what we should
of
do.
convenient in a way, have it as an object, because the underlying packet should know how those ports are being merged together. So there's some port function that has to be run, and if it produces the same result, then there should be a wire created, right? So in a way, if the function takes in as a port object, it can be queried with a bunch of functions.
Okay, well, fine. Then we can't use the name port. Okay.
Agreed.
So if it's going to be port object or something like that, you could potentially use that as an internal symbol.
Probably needs to be diagram port.
Yeah, that makes sense.
Somehow namespace it to.
Yes, I think that makes sense.
To diagrams. It's not the same thing as vertex port.
Right. So if it's diagram port, I don't see a fundamental problem with it, but let's keep going. Okay, so here we've got this, and this is saying, I don't quite understand. First of all, why is this name repeated on this wire?
Because it inserts all of those wire diagrams, like an identity diagram is inserted there. So, and here by default, it also puts a label on the ports for that identity.
Presumably we could prune this, yes? So that we only have one label on that wire.
Yeah, just a matter of how you, provide options for those.
Nick,
Right.
is there a way to specify with options that there should only be
Well, for
one
the
label
for
on the wire?
for the global option, you can it's only convenient to either turn them off completely or have this.
No, I understand, but I'm saying what we want is one label per wire. Right, so I'm asking, is there a way to do that? Do you know technically how to do that? Is that already a thing or not?
It's not a thing. It's a bit problematic because it's arranged into a grid. So in a
I
way,
know.
there's inherent dividers between those.
I
So
know. So it
yeah.
requires an additional scan to say on this wire, and you know it's one wire, does it have
Yeah.
multiple labels? If yes, prune some of the labels.
Yeah, that can be done. It just haven't been yet.
Fine. Okay. Okay. I mean, we have had no graphic design done on this. Let's please, can you guys get a first iteration of graphic design for this?
Okay.
Do you mean like the shapes of the diagrams or
Yeah,
color?
the colors, the shapes, the fonts, the usual nonsense.
Okay.
Right? I mean, it's just this will look beautiful when it has, you know, the skeleton is great here. Makes sense?
Yep.
Mhm.
I mean, if we want, maybe we can see if Jeremy happens to be available. See if we can get some input immediately.
Okay, let me
Carla,
hear.
could you do that?
Yes.
Okay. Oh, this is looking interesting. Okay, I don't understand. Okay, what does this mean? So tensor diagram, what does this mean? Can you explain this to me? 2, 3, 4, I see it's contracting across index 4. How do I know that it's index 4? It's A2 there. How do I know it's index 4?
Well, there's no
B.
dimensionality checks, right? It doesn't that actually checks whether those dimensions are compatible. But yeah, it just sees the dot product, and there are two array and matrix symbols, turns them into the diagram, and composes them.
But
Right.
what does the sub2 mean here?
That's the dimension provided. So yeah.
So this is a very weird construct here, because if we're thinking about
I guess
as
that
an
means
array
the
symbol. Go
second
ahead.
slot of B. So it's contracting the first slot of B, and B2 and B3 are free. The
Yeah,
problem is
so
that it's not looking at
not
dimensions.
the first slot, is it?
Yes, dot contracts the last of the first and the first of the second.
But how does it match then? Because this is dimension 4.
Exactly. Nick is saying that he's not doing dimensional checks.
Okay, but he should be.
He should. Exactly. Yep.
Okay, fine.
Totally.
So let me just for the sake of
Exactly.
being not so confused, let me do that.
Yeah, change
But
the last one to 2, for example, so that there's no repetition.
Well, we could, but I mean, why? I mean, I don't understand. There's two issues. There's the dimension and there's the slot number, right? This
Right.
B2 means slot number.
Yeah.
And why is that saying R3 there?
Well, that's now that corresponds to dimension 3.
What is dimension 3?
The second slot of B.
But why is it R3? It's just an index.
Well, because array symbols have a type, right? It's real complexes. So takes that type.
But why is that the right type for the index? I mean, that's the value of that array element, but the index is just an integer from 1 to 4. And this thing here,
how it's presented in string diagrams for tensors. The wires are types, so they're either reals or complex numbers. They have a dimension, so you associate them to an actual field, like a reals or complex number. So yeah, it's standard.
I guess he's trying to say that this is an index acting on a vectorial space of dimension 3.
I'm totally confused.
So B is something with 3 slots, and each one acts on a different vector space of dimensions 4, 3, and 2.
So by acts on, you mean you can feed it that
Exactly.
by contraction, and
Exactly.
it will ingest it.
Yep. So you can have
Okay.
B multiplied by a vector of dimension 4, another 3, another 2, and it will give a
Although,
number.
what do you mean? Is it a vector? Is it a covector? What the heck is it?
There is no distinction at this level. It's all lists in our sense. There is no
so
up
we
and
don't
down.
have to make that distinction of covariant and contravariant indices and so on.
At this level, apparently, I mean, I don't see the freedom where to put that.
But should we have that distinction? I mean, in order for it to be useful for tensor algebra, should we have that distinction?
Well, I mean, to be used in the standard GR computations, that would be useful. But I mean, even our array symbol doesn't have that.
Right. But so, okay, so we should think about how to include that here. I mean, so array symbol doesn't have that because why? Because it's always Euclidean space where it doesn't matter, or what?
Effectively, yes. You can think that it's always working with orthonormal bases. Yeah, Cartesian space, orthonormal bases. So you don't worry. I mean, you worry about covariant and contravariant when you have a metric which is not diagonal once, because then depending on whether you have the indices up or down, it means you have contracted a metric. And if the metric is not the identity, then it's very important.
Okay, but so in all of our array stuff, we don't have a notion of metrics. We don't have to
Exactly.
worry about metrics. But what would happen? I mean, just so I understand, if we were going to the next level of sophistication where we actually do have a metric, what would everything look like? Then
Well,
our dot, we would need a generalization of dot, or we would need a generalization of array symbol. We'd need something that is called, I don't know what would we call it?
not necessarily. So the important thing is that you contract always an up and a down. That's the important thing. And so perhaps dot doesn't have to be generalized if dot can do these checks of, oh, I'm contracting the proper up and down indices.
Right. So, I mean, and I think you did this in exact, and I don't know how, is there a wrapper? I mean,
Well, what I do is in exact is having upper indices as A, B, and lower indices as minus A, minus B.
Yes.
So a tensor TAB V minus B. That would be a contraction. But yes, here, I mean, you always have to, okay. So this is going into a tangent. So the index themselves numerically, I don't think that's the proper thing. So whether it's up or down is a property of the object itself. B needs to know which are the indices, and then you have names.
I see. So in other words, more it would be something like, I mean, I don't know, does array symbol have more than 2 arguments or not?
Well, it takes the dimensions. And the domain. You can say complexes or symmetries, etc.
Right. Okay. So I mean, in a sense, what is the generic term for covariant versus contravariant?
I call it, I mean, it has many names, but I call it the character of the tensor.
Okay. So I mean, let's say, tensor character, arrow, 1, -1, 1, whatever it is.
Exactly. Yep. Something like that.
And then what would happen? And if we added such an option to array symbol, then the main thing is we get errors if we're not going covariant to contravariant. Is that right?
Yes, exactly.
And
does the up indices just become the input ports and the down indices the output ports in terms of diagrams?
That could be a possibility. So something needs to remember some sort of duality.
How does it normally work when people make tensor diagrams for general relativity? Like,
Okay, in general, because the metric is symmetric, once you have contracted, it doesn't matter which one was which one. And so the diagrams, the birth tracks, etc., don't have a direction. The important thing is that at the time of contractions, you check that one is up, the other is down.
But
Then
when you compute the numerical values, don't you have to include a metric?
well, the numeric, okay. So imagine that you are going to contract two indices down. That doesn't work, but you can fix it by multiplying by the inverse metric. That raises one of them, and then you can contract.
I see. So once you're going up to down, yeah, there's no metric involved. It's only to do the raising.
Exactly. The metric sends down, and the inverse metric sends up.
Right. So this is like a raise or lower array or something.
Exactly. Yep. And then you need to know with which metric did you do it. But
Yeah,
standard in the standard computations, there is a single metric. But some people work with two metrics, like conformal problems, right? In which one metric is a multiple of another one. And then you have to be super careful about which metric did you use to raise or lower.
Right. But so the whole point is by default, the thing would just give an error if the characters don't align correctly.
Exactly. Dot should just check that the characters are incorrect. Some other functions should worry about raising and lower.
Yes.
Because otherwise we have to insert a metric in dot. I think that's too much.
Right, but then what would happen here is raise array would take the array and, wait a minute, what numericalizes this array? Because at some point then it's got to carry around with it. Where does the actual, contraction with the metric actually happen? Because this thing here is still a completely symbolic array.
Yes. So raise array could take an array and say contract in the index 3 with this metric.
I see what you're saying. So raise array could basically turn into array symbol
dot
of
something, yeah.
Blah 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 dot metric tensor, whatever that metric is.
Exactly. Yeah, and it has to know in which index it has to be contracted.
Yes.
Because dot by default will contract the last index of the array symbol.
Right. So this is probably a tensor contract.
Exactly. Yep.
So raise array and then it's index I. And this becomes a tensor contract.
Correct.
Well, this doesn't look too hard to implement. Maybe we should do this.
Well, no, a metric is already a tensor. It's all about how you compose them together. I think more general notion is just a basis. Some indices have a basis, and if they're not compatible, you want to convert one to another, or rather to a conjugate basis, because you contract basis with its conjugate. It's like two wires of the same type coming together. That's when the contraction is allowed.
Fair enough.
Yes.
I think we should try and figure out this design. This looks like fairly low-hanging fruit to me. And I think it'd be very useful for all sorts of general utility things. Yeah,
the problem is that we have a ton of linear algebra functionality. So designing the object may be relatively simple, but propagating it through the functionality, that will be a major project.
Yes, I understand. But if all that's happening is, I understand. I mean, we've got to derive a bunch of relations, which is what we've been doing for array symbol and so on. But I think it's a worthwhile thing to do. And we should probably, Carla, that's probably something to add to the GPL.
Okay, Jeremy's here.
I noticed that. Thanks. Yeah. So Jeremy, we're trying to make this beautiful.
Okay.
Which it clearly isn't right now. And
does that have a relation to anything else in the system that it should match to?
Well, it's similar to that stuff in the Lambdas post that I just did.
Yep.
And I think, well, Nick, you should say, it's always going to be boxes and wires. Is that a true statement?
Well, the shape of the box can change. It can be circle, maybe triangle.
Meaning something different or what? Does it mean something different, or is it just a vertex shape function?
It is like a vertex shape function, yeah.
Right, so it has a default shape, and then it could have other more exotic shapes.
Yeah. Just conventionally, maybe like things like spiders or circles. Maybe you want triangles to have a copy. Things like that.
But so you have explicit symbols that mean, a cup. This is where you have your cups.
Yep.
Well, those things. Okay, so that is a non-box, so to speak. And
Yep.
the copy right now is not showing anything explicit, right?
Yeah, but this is just a shape. Just all different.
These are all actually boxes,
Which
with a
have been
shape
made to
that-
look like they don't have
wires,
boxes, so to speak.
Yeah.
and it's because they behave. These behave sort of like wires in different relations.
Right. So this would be a typical example. Right composition here is composing. This is very cool, actually. Is composing this thing, which is basically a box, but happens to be a box that connects this to this, and so on. That makes sense?
Yeah.
So how did this spider, that's a spider, right?
Yes.
Yes.
And how did that spider get identified? That spider got identified because there are multiple C's there. Is that correct?
Yeah. Well,
It
by
has
default, it either has to be more than 2 ports, or maybe they're incompatible, like that X, because it connects 2 outputs of C. It's created there by default.
And this is
So
because it's
otherwise it
using
would just be a
diagram
straight
network.
wire going from one thing to the other, from an input port from an output port to an input port, and so on.
Yeah. So there's
But
can be an option to get rid of that X, just to have a shape with 2 arrows. Edge shape with 2 arrows.
But the point is, this is a third completely different way to compose diagrams than the vertical and horizontal compositions.
Okay, so let me just understand. So basically what's happening is either data is sort of flowing through these wires, sort of, and having to match wires to wires.
In a very grid-like way of building it up with vertical and horizontal compositions.
Right. Whereas this is everything goes. Everything can connect to everything.
Connect everything that can be connected, even things that wouldn't normally be compatible, like 2 outputs.
Right. Well, presumably there should be compatibility rules that you can specify in diagram network to say what should actually connect and what shouldn't.
Nick, how are you determining that right now? Is there some internal?
That's what this port function I was been talking about. It's just like a function that runs on ports and produces some canonical value of it. If it's the same for multiple ports, that's where they're being unified. But you can customize it and make it a bit more complicated.
Okay, but when they're not unified, like if these things weren't allowed to connect, what would happen? Would it just be an error, or would there be 2 wires hanging out?
They should be dangling.
Yeah, like that D is dangling, right? It's not connected, but the spider is also created there, which is not necessary, but visually it is created.
But so here, I mean, do we like
you only aren't creating a spider when it's connecting exactly 2 ports together, because then that's just an ordinary graph edge.
Do we like the fact that we're getting boxes turning upside down and so on? Or should we be rotating these things? Or if the box was a circle, obviously it can be any way around. But on the other hand, then it doesn't, in this representation, it's clear what's an input port, what's an output port.
Nick has been, I've been discussing some proposals from Nick that diagram network might allow all of the ports to kind of just float around the boxes. Right now, there's still maintaining this distinction between the input and the output. And so it's twisting things around based on that. Arguably, all of the wires could be just radially spaced around the boxes. And then
with arrows. I think there are use cases where you definitely want to see what's input and what's output. I mean, this is getting a bit wild here.
Yeah, and a lot of that is getting twisted because of having this distinction between input and output.
Right. And I mean, I don't quite understand. We've got blue lines here and we've got black stubs here and so on. That doesn't make a lot of sense to me. Right. Those are stubs of those connections, right?
Nick, is that the ordinary graph edge style?
It is just default edge style.
Okay.
So there's some kind of I guess it's using graph styling to connote that there's a different kind of connection.
So let's just, for Jeremy's benefit and others, let's just talk about what we roughly need here. So I mean, the thing would have a vertex shape function that allows one to do whatever one wants for this, but we need a default. And when it is on a grid, it makes perfect sense to have the boxes be rectangular boxes. Do you agree, Nick?
It also depends what you want to do with them. Sometimes maybe you want not symmetrical box to track how you operate, or maybe you want to reverse the diagram, and the shapes should also reflect that.
Well, do you want by default?
For example, the transpose of a diagram rotates at 180 degrees. So sometimes it's nice to have one of the corners be non-symmetrical so that you can represent the transpose of that diagram by just rotating which corner.
But is that what you want by default? Should you have a dog ear by default?
I don't think. I think if you make a diagram out of 3, then not. It would depend where the diagram is coming from. If you created one from the tensor, maybe it should be by default non-symmetrical.
Well, but okay, then what would it look like? We have to have a shape.
Have some examples, right? With the rounded rectangle at the end.
But rounded rectangle doesn't give you an orientation, does it?
No, it kind of it will be single.
I see. Rounded like that.
Yeah. So that A node with the corner on the top right represents the vertical flip of the original.
So this is a flow.
Node.
It's kind of like a proto arrow, so to speak.
Mm-hmm.
Jeremy, do you have any particular thoughts about this?
But it's mainly to communicate in versus out, in orientation of in and out.
And I think also left-right orientation.
Okay.
Yeah.
It's interesting. Yeah.
It's so that vertical reflections, horizontal reflections,
Mm-hmm.
rotations, they all get tracked in that shape.
But so is this like the analog of a directed graph versus an undirected graph that we have? I mean, what determines whether we have a regular box or a box with an ear?
So like in the tree case, conceivably the output could format like identically to a tree.
Well, no.
The leaves
I mean,
and the non-leaf nodes.
Yeah, but why? I mean, it's not represent. I don't understand. I'm just asking. In this case, should this have the dog ear or not? When should there be a dog ear?
I think this is representing the symmetries of the thing being represented. So for tensors, it will be clear. But for functions, for example, if you have a symmetric function, then it's natural to include that symmetry.
Okay, but these generically, a function is not symmetrical at all. Every argument means something different.
Right. So then it would be nice to have something that in general is asymmetric, so that if you flip it, you know it.
So in other words, you're saying the generic case
which that rounded rectangle shape.
Exactly. I think symmetric representation should mean the object is symmetric itself.
Well, maybe then it should have 2 dog ears to make it consistent, and then it always has a flow down, and so the asymmetric case would have 1 dog ear, the symmetric case would have 2.
Right.
Does it matter where the dog ear goes? I mean, you've got bottom right, but somehow top right feels normal to me.
Well, the problem is that we want it flowing down, as in the
Mhm.
input comes in at the top, the output goes down at the bottom. Whereas
Yep.
if you put that ear there, it feels to me more like an arrow that's sort of pointing down. I mean, in other words, if you put the ear there, it seems like an arrow pointing up.
Okay.
The relevant cases are 1 ear, 2 ears, and no ears.
When
Now,
would there be no ears?
When there's not supposed to be any, a vertical reflection and a horizontal reflection, both should not,
I see.
th-
But then,
that
and then there's
symmetry
also the
should be
circular
there.
case.
now,
Yes.
of course, if the numbers are there, that the numbers can also solve the symmetry.
Right, but to me, it makes more sense to have 1 ear, 2 ears, or 4 ears. A rounded rectangle, basically.
Mhm.
We should just decide which array symmetry corresponds to each shape.
Okay,
Yeah,
so no
I-
symmetry. What are you proposing? You're proposing 1 ear to the bottom right corresponds to no symmetry. Is that right?
Yes.
And an ear to this side and this side means symmetric in the output. The output is symmetric. Is that right?
Yeah, and the input.
It's a horizontal symmetry.
Yeah, okay. And ears on all sides means it's symmetric, both that input and output are symmetric, as well as symmetry. So I don't quite know how you would do input and output.
But you could also do an ear on the
there and there.
Yeah.
2 ears there. That would mean symmetric. Input output is symmetric, and but there isn't.
So that shape is symmetric vertically.
Yes. Okay.
There's going to be like some kind of notches at each port, because if there are many indices, many ports on the diagram, and they're symmetric in those particular pair, you should somehow indicate that it's symmetric in that pair. So you just make some notch in there so that if you assume that you permute them, nothing changes.
Has anybody done this? I mean, like my friend Predrag Svetonovic has been doing, the bird tracks his whole life, so to speak. And I mean, have you looked at his? Does he have a way of representing this, or does anybody else?
Well, I have seen some of his diagrams, and he does take into account the symmetry. So the I don't know how to call it. The graphic object does represent the symmetry.
Right.
For example, I remember that the metric, because it's something you continuously contract, is something that even becomes a point, because once you have contracted, you don't care what it was. But
Right.
all of the tensors do keep shapes representing their symmetries.
Even the point, when you contract everything into a scalar, if that scalar is complex, it may have like a slightly different shape. Or at least there's some, it's not about even reflection of the diagram, there's also like direction and conjugation.
I have a hard time finding a copy of this. Weird.
One of the sources we've been looking at is picturing quantum processes, and there they use trapezoids, where one of the parallel sides is shorter than the other.
Well, okay. So look, get a collection of these shapes, and let's figure out what to do. Okay. But in terms of, so we need the shapes. We need a library of shapes. Probably what we should do is like vertex shape, like the vertex shape option that I'd forgotten existed. We could presumably use that vertex shape option again here with a different collection of named shapes. Does that make sense? Like here, well, I thought we had named shapes for this. No, we don't. We have arbitrary
Right.
shapes.
It's in vertex shape function where there's named shapes.
I see.
Rounded rectangle would be a useful primitive, honestly.
For what? For everything?
Just the graphics language, yeah. Just general graphics language to have a rounded rectangle instead of
Well,
just rectangle.
we have that with rounding radius, but to have, I mean,
Yeah.
that's a good
Not-
suggestion. That
Don't
maybe
we have
So
something
that-
called stadium?
No, it's frame has that, but not rectangle.
Oh,
it
So you'd
doesn't.
have to do an inset of a frame or something. As far as I know,
Wait, sorry, is the claim that rectangle doesn't support rounding radius? Or
Yes.
whatever the option is called. No, I think it does, doesn't it? I think it supported it before frames did.
I thought
really?
so too.
I
Okay,
believe
never
so.
used this.
Yeah.
Okay.
Can you look at the stadium's shape?
Up.
Primitive?
Sorry.
well,
Yeah, it
well,
supports it
clearly
though.
worked. It
Yeah.
clearly worked.
What the heck? What's going on here?
The
radius
rate,
small.
yeah, to put it as, yeah.
Yeah, okay. But one thing you're suggesting, Jeremy, which I think is not a bad idea as a design idea, to just have a primitive called rounded rectangle.
So,
rather than
sorry,
having
can you
to
look
do
at
this.
stadium shape?
Yes. And what do I do?
I mean, but look at the rough page, because this may be.
Maybe this is just dumb and yeah, I mean, this is basically we should have called this rounded rectangle. Okay, can we bring that to an LCC meeting?
I mean, this requires all corners rounded.
Yeah.
This is different than rounded rectangle. It's more a geometric structure, right? Where you have radius, you have disk at the end with a radius R. So it's completely different.
Okay. Well, but it seems like rounded rectangle is something we already support. So presumably I can say, Charles, I can say area of rounded rectangle. And
No,
that's
you don't.
wrong. That's just wrong.
Because
That's bad. Why is that wrong?
well, because we consider that rounded the rounding
Oh.
radius, we don't support it as a geometric object.
Okay, I think this is a bug. But maybe what we should do is have a rounded rectangle that is both geometric and visual, so to speak, that does support this correctly.
Yes, can do that.
I mean, clearly you can do this given a single rounding radius because, you know, in the stadium case, presumably we can say exactly the same thing, except that it has slightly bizarrely different is the rounding radius the same as the notion of a radius there?
And no,
Why not? I mean, okay, so there's that. And now if I say graphics of this,
so you can just think about it as a rectangle, but at the end we have disk, which is completely different than rounding. Sorry.
well, and also the way that this is done, it's x1, y1, x2, y2, rather than x1, y1, x2, y2.
Well, from a
I see.
geometric
I meant the other
perspective,
way
we
around.
deal with point, right? So
Yeah, so this is more like a thickened line.
Yes.
Mhm. Yeah,
Can
I
you
was
bend it
confused.
like a line with a cup form?
No. You can do that with a tube, right? What is
You
what
can
is the
do this with a
primitive?
line as well. Yeah, cap form round will do this with a line, but it can't imagine the area works.
Right. Okay. Anyway, let's go back to this. So can we please get a library of what, you know, what's out there of the ways that people have represented these things? And then, you know, we probably need to pick for diagrams, what will be the default color for these things?
Well, you suggested using your Lambda blog as a starting
No,
point.
that was a weird pink. I mean, you're using a weird pink for this, just as that uses a green. But I don't think we want, you know, we don't want everything deeply pink, especially as the areas of color will be quite big. Making sense?
Hmm. Yep.
And clearly the borders should not be this strong. And
Right.
I mean, you could fix that immediately. Nick, just put opacity and thinness in the borders.
All
and
right.
use, what's that?
Okay. Okay.
And then for the font, just use the the text font that we use for like labels and so on. Does that make
Okay.
sense?
Yeah.
Now, these lines here are I was going to say, well, I see. This is just using the tree coordinates. Okay, we should look at some other things here. So this is
Is there a label style, by the way, for the text overlays?
what do you mean? These things
For,
here?
yeah, especially the ones over the lines. I want to try like haloing and some other stuff. Just don't know if I can get to it
Oh, yeah. You're just asking in this
in the
setup.
spec. Yeah, right.
Nick, is that the case? Is there a style, an edge style?
Well, the way styles work right now, you can specify the port style, and it kind of propagates to the wire.
Okay, but what Jeremy is suggesting is, could we halo? Several of these things could deserve to be haloed. So, for example, here, I mean, haloing these lines would be nice.
Yeah, and definitely haloing the text over the line.
Do tree of some association, some simple association.
You want to be careful with haloing that you don't obscure the arrows. I mean, there was one case where the arrow happened to coincide with the line, and so it depends on which one's drawn the highest, but you could obscure the arrow, I suppose.
How do you want me to do the tree? What do you want me to do?
That's fine. Evaluate that.
I see. You're
like,
labeling
like
those
that.
with haloing.
And if they overlap and get like tons of typewriter ink overlapping each other.
Right, but for example, in this Lambdas thing I just did, the we wherever it is. Oh, where is it? There we go. Here we did haloing for those line crossings, which looked really nice. Now, by the way, Nick, the technology used for this, is that do you have examples of that here? Is that what's being used here, for example?
Yes, though you need another step. Like if you rerun it, I think it's gonna the style change, right? And then you diagram arrange this network. The result of that, do the diagram arrange. You get a grid-like diagram back. Yeah, and then what we see in the block is just some smoothing out and rotated version of it with some styles changed slightly.
But the smoothing out is something that should happen by default, yes?
I'm thinking about it, yes, to put it by default. Yeah.
Because I mean, right now this is made from a bunch of rectangular puzzle pieces.
Yeah, just separate line segments. They can be just extracted turned into a single big one and smoothed out.
Okay, so one thing I would like to ask, I mean, how do I get something out of this diagram? How do I get an expression out from that diagram?
An expression like a...
Well, like a lambda in this case. I mean, this diagram represents an expression. How do I get the expression?
I don't remember if like diagram extract is implemented or not.
Well, we have like a diagram function maybe, or diagram tensor. That's more like it. Of course, there's some diagram decompose, which just shows all the individual pieces.
That's not exactly simple. How do I get, I mean, this represents a lambda. And the whole point is to have a diagrammatic representation of these things. In fact, there is the lambda it represents. So how do I get back out the lambda from the diagram?
Well, for it, I think the only way to do it is just to have specified function that knows that you want a lambda. And I don't
Okay,
have
but I mean, isn't there a representation? This diagram represents a thing in functional form, and it's not this. This is the
Well, try
tensor.
diagram function. I'm not sure what it's going to do, but it's another representation that we have, general. So it's also going to be, it's some kind of a function.
What the heck is this? I mean, can I apply this to something?
Maybe it doesn't need, I think it's 0 arguments, so no argument application. Yeah, it depends what kind of annotation you have for those pieces. Maybe
But
that's.
I think that these diagrams should canonically represent an expression. Why not?
But how you can do it canonically? It's like, what if you have a loop? You have backward wires. Those are
I
like
see. Your point is a diagram, a tree, an expression is a tree, a diagram is more general than a tree.
Yeah, I think the only general thing you can do is a tensor, because it's like linear algebra is very generic string diagram representation.
But the tensor we just got here is a total mess.
Well, that's because the diagram is messy with all those explicit identities. Without diagram arranging it, you can try a diagram tensor before you arranged it. Just this one, yes.
I think what we would need here is some sort of notion of product and a notion of contraction, which in the case of tensors is tensor product and tensor contraction. And then there will be objects with letters that indicate that the objects are the nodes and the letters are the ports.
Yes, but I don't understand. What should this do? In the tensor world, what should this do? And what do the copy things mean? In the tensor world, how do you copy an index?
How do you copy what?
An index, which is what's happening here.
Well, there's a linear algebraic representation. It's like some generalization of your symbolic identity. How's it called? In the symbolic arrays, there's such a thing.
For copying indices?
I mean, once the contraction has been performed and we have these edges going from object to object, the index itself does not matter. I think the beauty of these things is that you don't need dummy indices. Yes. Because those are represented by the lines. Edges.
Right.
So the names do not really matter.
I understand, but what does the copy mean here? Because that's an index.
Oh, look, it's like
that's
a symbolic.
If you copy if you click on the object and copy the object, I think it should just get the object back with the name, like the tensor T.
Right, but okay, look, here's the comment. The Einstein summation convention, for example, is one way of combining indices.
Exactly,
lower to upper, whatever. But let's say you have 3 indices, mu. In general, there is a spider to combine those. See what I'm saying? Am I right, Nick and others?
Yes.
So sort of the Einstein summation convention is just a very degenerate, 2-legged spider.
Well, the Einstein convention is 2-legged when you insist on the up and down contraction, which is what is needed in linear algebra. But if one can generalize the Einstein convention to just say, contract everything that is repeated. Even if it is repeated 4 times, fine. Or is it repeated once?
And when you say contract every time, you mean take a trace of some kind?
Exactly. Yeah. I mean, our trace, our TR function can specify the number of levels you can contract, which may be 4. It doesn't have to be 2.
I see. So, okay, so that's a type of spider. I mean, right now you are representing these spiders in some arbitrary way, correct? I mean, these spiders that you're giving here could mean anything. except that these ones are known to be copy spiders, aren't they?
No, those are application. This is the lambda.
Oh, okay.
The white are spiders, and they have a tensor default representation as a tensor. Those are like a symbolic identities, right? As soon as you turn it into these tensors, you can still do
Oh, I see. So
contractions.
that's these identity tensors here.
Yeah, this is just maybe a single wire, but there's some higher index identities there with more indices, like ABB, and that's
Okay, so let's just we're kind of running out of time, but let's just look at okay, so for quantum circuits, this is just kind of directly how this will work. What level of spidering happens in quantum circuits? Or is it
Quantum
always,
circuits-
is reversibility required that you never have anything more than just individual connections like this?
No, you can put your all the spiders in the quantum circuit are explicit. You can make a spider, which is just another operator that you can put into the circuit. It's not created automatically.
So I think I'm a bit confused about the concept of spider. Spider is when we have an index repeated 3 times, for example, right?
Yes.
It can be from
Well-
one to many.
So I think that in linear algebra, in quantum mechanics, we also use linear algebra. And once we are in linear algebra and we impose invariance under changes of basis, contractions have to be 2.
Yes, but this is a generalization.
You can make a tensor so that each contraction becomes like if you have 3 indices to contract, you can make 3 binary contractions given a spider. And now we just have an explicit tensor that represents a spider.
I don't know that. Okay, let's talk separately about that. I would like to know about that.
Okay. I mean, this is, so just,
I mean,
yeah, go ahead.
like spider diagram, that I think there's a spider diagram symbol. Right, Nick?
Yes.
That's another one of the special diagrams. It's a box that somehow is pretending to be a bundle of wires.
It's a circle, yeah.
Okay, so in general, if I say permutation diagram, oops, and I say, don't we have a random permutation function?
That would be random sample.
Random, yeah, just give it a
Oh, yeah,
random
yeah.
sample, some range.
Yeah, so then if we say permutation diagram of,
Just that, give it just this.
oh, okay. Cool. Except for these stupid spaces here. I don't know what those are caused by. Now, for example, here, having haloing would probably be a good thing.
Yep. Though maybe there's also a difference between permutation and some kind of braiding, like in knot theory, right?
What's the
Here you don't
difference?
necessarily distinguish between whether your wire goes on top or below another
Oh,
wire.
yeah, right. Well, how do you represent the braiding thing? Or you can't in this case, or it doesn't care in this case.
Well, yeah, you don't. In the diagrammatic computation by itself, there's no default representation. But if you assume some linear algebra, there's some braiding representation. So you can represent braiding operate as a tensor. It's basically like permutation with some minus signs, for example.
Okay. Jose, do you know about that?
No, I think I'm confused now.
I am also confused. Just okay. I just to review quickly here. What about category theory diagrams? Are you
Well, so you already like a category theory, a monoidal category.
These are
Well,
diagrams of morphisms in a monoidal category.
but in the sense that this is a morphism here.
Yeah.
Yes.
And
the fact that you can have a morphism that takes multiple inputs and multiple outputs is because the multiple inputs are just tensor products of identity diagrams.
okay, but the operations of category theory, do we have functions? I mean, so right now, what you have here is basically a representation of diagrams. Now, what operations do we get to do on these diagrams?
So, I mean, like the categorical like composition is diagram composition. And since we're in a monoidal category, you also have diagram product, which is like a tensor product.
But so what, so to speak?
Well, that's like the default way that you build up diagrams is with vertical.
Yeah, I understand, but I mean, how do you use?
I mean, like for just for the category theory, or in some.
Yeah, I mean, like we have a bunch of these functions here.
Well, those are like named abstract for a reason, right? They just like represent abstractly what it is. You rarely can do anything specific with them.
But I mean, there are all these functions that you can apply here. So can we represent a diagram like this?
Yeah, it's like a diagram network in that case.
Okay, with these morphisms. So, but I don't quite understand, because the morphism normally is the thing in the middle. It's the thing that is labeling the edge here.
Yeah, it's kind of dual to that. Yes.
So, but we need to understand, how do we represent category theory diagrams in this framework? Yes.
Yes, perhaps. I can think about like some kind of dual graph representation when you reverse what is the edge and what is the vertex.
Right, because these things, if these things are representing morphisms and these are representing objects, it's sort
Stephen,
of.
I put a link in chat. And just keep scrolling in the diagrams until you find an example of full labeled string diagrams. Keep going. Keep going. There. These are what we're representing using diagram.
Okay. Well, but can we please try to figure out how?
Specifically monoidal categories.
I get it, but we should be able to do arbitrary category theory diagramming with the system.
Yeah, I believe so.
So that's a use case, is category theory. Tensors and general relativity is another use case. Am I right? The group theory stuff. Maybe you listed that at the top.
There's a list at the top.
Okay. So
Examples.
let's just. I don't understand the Feynman diagram case. How would we actually use this there? The objects would be interaction vertices in the Feynman diagram. Is that correct?
Yeah. I can send you maybe an example.
Yeah, can you? We should wrap up soon. But I mean, but then, the whole point of Feynman diagrams is they represent expressions. The diagram turns into a computation. So the question is, how do we take this? I mean, it's the same thing as evaluating graphs, which I believe we have another discussion about. Right? I mean, trees, we have things like treefold, which evaluate trees. Am I right?
Yep.
And we have a proto, we have WFR functions for doing essentially graph fold. I don't know whether Charles is that on your roadmap right now, graph fold and so on, Charles?
Yes.
I mean, we understand how to do it for DAGs, but we don't have a special representation for DAGs. So it's a little unclear, I mean, is graph fold something we're going to look at soon, or what?
I think this was on the agenda for the last graph evaluation meeting, but we didn't get to it.
Okay, but what's the relationship between this and graph evaluation?
I mean, Feynman diagrams.
Oh,
Or the Feynman diagram is also like very specific representation. So given a diagram, you need to have a lot of extra information.
what the heck is this?
It's just the first example I found that I had.
It's an electron self-energy diagram. I understand, but what are all these things doing?
Those are just outlines. What are the actual diagrams there in that composition? So it contains a composition of 4 things. There's some
I see,
preparation.
an incoming edge, a vertex, an outgoing edge.
Yep. And you
How
can
do
customize
things like
those.
the fine arts package represent this stuff?
Well, some kind of graph, maybe some graphical, very similar graphics.
But what's the advantage of using a quotes diagram as opposed to a graph here?
That's I'm not sure about. No,
Okay.
there's not really an advantage. All you care about is just the topology, which is a graph, and then you take it in to construct some kind of amplitude.
Okay. What is the Penrose notation? That's a tensor network, right? What's the difference between those two?
It's a diagram network essentially. It's that way of composing diagrams together when you don't care about whether there's multiple contractions happening. Not.
But isn't that the same as tensor networks? Or am I confused?
It is, yeah. It's kind of it's the same. It's just
Okay,
when you
so-
use this particular framework, you use it. You make a network like you write a Penrose notation.
Okay. And bird tracks is the corresponding thing for group theory, right?
I believe. Yep.
I still want to know. I mean, like in bird tracks, okay? I've used bird tracks, admittedly, in 1977, so it's been a while. But you know, the result of bird track stuff is you compute numbers, right? You're computing group weights and things like this. Am I making sense? So I'm trying to understand how we go from these diagrams. You know, to me, these diagrams, okay, we've got expressions which are tree-like things. This is an attempt to go beyond tree-like things to allow the possibility of loops and so on. And you know, this is an alternative. It's a generalization of expressions. But how do we evaluate this? Like an expression has the feature that we can evaluate it, and it becomes another expression. How do we do the analogous thing here? Just like with lambdas, we know that we can evaluate the lambda, you know, because it does beta reduction and produces some other result. So how does that merge with this picture? I don't. There's no reason it can't. I'm just trying to understand how that would happen, because that's
Yeah,
where
well,
this becomes really useful. You can deal with things in a sense at a diagram symbolic level, where you're just manipulating diagrams, and then in the end, you know, you turn that into actual computations, and the answer is 7 or something.
I think the analogy with arrays and matrices is important here. So if we have contractions and tensor products with symbols, there is not much we can do other than symbolic operations. But if we now replace some of those arrays by matrices or arrays, then perhaps some part of the computation can be done, perhaps all the way until a scalar.
Right. But I mean, something like a Feynman diagram represents a bunch of Dirac-Gauss matrices and you know, and polarization sums and you know, group sums and then integrals. And the question is, you know, so that diagram, you know, if we were to write out that diagram, it's been a long time since I've done this, but you know, it's 1 over p slash, which I don't even know how to write in our system, minus m times, you know, actually I should have said, well, you know, that's that line there times, you know, there's a gamma mu there, which again, it's like, and then there's some 1 over, k minus p squared, et cetera, et cetera, et cetera, et cetera, et cetera. And then this whole thing, what this actually represents is some integral over, this loop has an undetermined momentum. So there's some integral over the, a parameter for this loop, and that turns into some complicated, 4 minus epsilon dimensional integral, et cetera, et cetera, et cetera, right? So my point is, this diagram represents some algebraic expression. And the question is how to get from the diagram to the algebraic expression.
Well, I think for each of those domains, there just has to be a specific function how to do it. Like maybe the diagram is generic and maybe it's annotated specially, like so that you would know that this gamma is some gamma matrix, right?
But the whole point is that my point is that it's exactly the same as with expressions. Expressions are generic. The tree structure of the expression does not say whether it's a plus or a graphics object or something else. So I think this is going to need the same kind of thing. Right? Just like you have.
Yeah. We have like diagram construction. We have purely diagrammatic operations that you can perform with them.
Right, just like we have operations on expressions, like at the head of an expression or apply something to an expression. Purely structural.
We need diagram rewriting, and we also need ways of traversing the diagrams.
Well, we need to know
for each of these applications, there's going to be different things like integrals.
Right. Right. Well, interesting. Okay. Anybody got further comments here? And so, I mean, the point is we got to understand how these applications are going to work before we nail down the final design for the purely structural stuff.
Yes.
Right. But the purely structural stuff looks like it's progressing nicely. I mean, I would recommend that we try and do the category theory case, which already was like, because that's, again, a purely diagrammatic thing.
You mean like support those category theory functions?
Yes. Yeah, I think so. And then, what we got to be able to do is to lift, category theory is a way of giving an outline of some mathematical type or other type construct. The thing is, can we lift category theory out of what would be otherwise, just like we can have a type, type signature representation of some function, right? Which doesn't say what the function does, but it says what types go in and out. I think there's a similar kind of category theory lifting of a computation. Does that make sense? And that's what we should be able to do. Lift out the category theory diagram. Okay, I gotta go. But this is progressing in an interesting way. Any last comments from anybody?
Nope.
Okay, see y'all soon.